All right. Thank you, Vipin, for the opening remarks, and thank you everyone for coming for this tutorial, for this workshop, both in person and those who are joining on Zoom. So the goal of this tutorial is to provide an overview of what is KGML and what's happening in KGML using examples of recent work that has happened in this field, which is evolving very rapidly in the last few years. So certainly this won't cover all of the exciting work happening in KGML, but will provide some illustrative case studies too. And we welcome feedback from the community. So we'll have some time at the end to take questions from the audience. So here is the agenda for today. For this tutorial, we will first talk about what is KGML and why KGML, what is the motivation for integrating knowledge in machine learning. We'll provide a multidimensional view to structure existing research in KGML. We'll describe some of the research methods, some of the research problems that are being explored in KGML, and finally conclude with summary and future directions. So as Vipin mentioned, we are going through some of the most exciting times for AI research as large-scale foundation models such as ChatGPT continue to revolutionize almost every aspect of our life. They are changing the entire landscape of products and technologies, especially in the commercial arena. They're driven by the needs of the tech industry. And given their success in mainstream AI applications of computer vision, natural language processing, where we have ample amounts of labeled data scraped from the internet, for example, there is a similar excitement in the scientific community to see if we can inspire similar breakthroughs of these large-scale AI models enabling a scientific revolution in problems in science that have huge impacts to society and where current methods, mostly numerical based, are lacking either in accuracy or in efficiency. This promise or this opportunity is especially likely or possible today, given that many scientific disciplines are transitioning from being data poor to data rich. Right? We have growing availability of scientific data of different forms in different disciplines. For example, simulations in climate science and fluid dynamics. We have observational data from satellites monitoring the Earth. We have images of organisms in biology. We have high throughput experiments. We have scientific literature as a large form of scientific data. So given this availability of data, it seems possible that we can inspire large-scale AI models to solve problems that really have an impact on science and society. To the extent that some have even referred to the rise of black box AI models, models that are solely reliant on the supervision contained in data as the end of theory. Right? So the question is data the key enabler to scientific revolution? If we provide lots of data and lots of compute, would large-scale AI models replace existing scientific theory-based models that have been the workhorse in many scientific disciplines for advancing our knowledge? This sentiment keeps resurfacing, especially in mainstream media, at different points and at several points of time, which is reflected in these snippets of articles. For example, in 2008, there was a Wired magazine article claiming that we have reached the end of theory, right? That we can fully embrace the complexity of large models back in 2008 and do away with the scientific method of starting with theories, performing experiments, analyzing results, and refining our theories. There is, in 2012, in 2022, you can see many other articles having a similar sentiment. And this is many times a reflection of how we exaggerate the fear or even the trust that we put in these AI models. What we find when these models are applied in practice in many scientific problems is that the reality is much farther from the truth. When black box AI models are applied in scientific disciplines, there are many case studies that show that they are not able to achieve similar scales of success that are possible in the tech industry, in the commercial arena. So it's natural to ask what is different in scientific disciplines that is limiting the scale of success possible in mainstream AI. And there are several factors behind this. Let me talk about two of the main ones. First, the nature of scientific data is quite different from what we have on internet scale problems involving text and images. In many scientific disciplines, the amount of data is really small, right? And it's available in modalities, in forms, in representations that are very different from text and images. Um, when this scarcity of label data is coupled with the complexity of processes that we are after to understand in scientific disciplines, where we have heterogeneity or non-stationarity in the processes, where we have multi-scale complex processes that keep changing in different regimes, in different ecosystems, for example. um, this coupling of scarcity of data and the complexity of problems makes current AI models, black box AI models, show poor generalizability, especially when they are introduced to out of distribution data. Right? This is related to problems of hallucination that you may have observed even in ChatGPT problems. The second major difference in science is really in the end goal in science, which is quite different from what we see in mainstream AI applications, where we have benchmark data sets, where we care about state-of-the-art performance using standard defined metrics. The end goal in science is to take one step beyond just improving predictive accuracy. In many scientific disciplines, we care about understanding the scientific processes underlying the system. Right? So we need to look beyond predictive accuracy on standard, well-defined metrics to promoting explainability, especially in a language that a scientist can understand, right? So that this can be used as a medium to discover new scientific theories. So given this high-level overview of what is missing in current black box AI, we ask if we can overcome some of these challenges by grounding AI models, AI ML models in scientific knowledge. And this leads us to this paradigm of knowledge-guided machine learning, which is reflected in this two-dimensional figure. On the x-axis, we are looking at the amount of data that is used by a model. On the y-axis, we are looking at the amount of scientific knowledge that is available in a discipline, which can vary in its form and nature. In this abstract 2D view, scientific knowledge-guided machine learning resides at a unique spot that uses both the power of data and the anchoring of scientific knowledge. In contrast to black box machine learning models that only use data and hence have are although quite agile and can ingest lots of data to change their functional forms, they are not tied to any underlying scientific theories. On the other side, science-based or theory-based or process-based models are really good when we have lots of knowledge. And when these, when the knowledge or the equations that they are built upon can be solved in a computationally efficient way. Right? But when we have some amounts of data and some process knowledge, knowledge-guided machine learning provides us an opportunity and a platform to use both these sources of supervision at an equal footing. Research in this area of knowledge-guided machine learning is referred to by several names, and on the right, we just have a list of some of these names that you may encounter in the literature. This diversity of vocabulary of terminologies is also a reflection of the diversity of research communities that are working in the space of KGML. So you would encounter terms like science-guided machine learning, physics-guided machine learning, physics-informed machine learning, physics-infused, physics-aware, and machine learning can be replaced with AI, NN, ML. Right? So you can mix and match these terms together. But all of these terms are referring to a common goal of bringing scientific knowledge and the power of data together. Our perspective article in 2017 was one of the first efforts to provide a roadmap for research in the space of knowledge-guided machine learning by describing some of the opportunities that we could identify back in 2017 of how knowledge and ML can come together. Since then, since 2017, in these 7 years, right, this field has grown exponentially. And earlier this year, we have put out a perspective article on Archive, summarizing our perspective on what's happening in the field of KGML, which will be used as a grounding for the remainder of this tutorial too. So just to highlight how KGML is a rapidly growing community, we have several workshops that are being organized by the community, and not just by us, on topics related to knowledge-guided machine learning. We have the KGML 2020-2021 workshops that were organized as part of the NSF-HDR program. We have the Bridge program on KGML that was organized earlier this year at AAAI. We have been organizing the Fall Symposium series on KGML at the AAAI Fall Symposium series, and we'll continue doing that in the future as well. So if anyone is interested in joining the organizing team, we welcome that as well. There are many other workshops on topics related to KGML that is shown over here. For example, synergy of ML and physical sciences, and more broadly in the space of AI for science. There are survey articles, for example, the article by Jared in 2021 that covers almost more than 350 papers that have been produced in this field from 2017 to 2021, right? So that shows how this area is growing. And we have several hundreds of papers published in KGML every year now. In 2022, we also came up with the first comprehensive book on knowledge-guided machine learning, which includes invited chapters by leading researchers in the field, covering diverse facets of KGML research from different disciplines. So this shows you the diversity of research happening in KGML. And given this diversity, it's important to provide a structure to this growing field so that we can understand what is common between different research ideas, concepts, efforts, and where are the sweet spots, right? Where are the opportunities for future research? So we in our recent archive article, we have tried to provide a structure to research in KGML using a 5-dimensional view. Each of these dimensions represent a different facet or a different aspect of KGML research that can help us situate existing KGML research ideas. Right? So there are different settings on these dimensions. And these settings are also not mutually exclusive. So you can even have combinations of these settings. We can think of these dimensions as questions that a researcher can ask, right, working in the field of KGML, to help them understand where do they lie in the broad space of KGML. So let me illustrate these dimensions very briefly, one at a time. The first dimension that we explore in KGML is by asking the question, in what format is your scientific knowledge available? Right? Is it available in the form of PDs? Is it available in the form of scientific laws, symmetries, knowledge graphs, mechanistic models, and so on? In the space of research in KGML, for solving the PDs, we have seen a huge interest and growth. PDs are almost like the universal language in most fields of science, especially in physical sciences. They show up in problems in quantum mechanics and fluid dynamics and many such disciplines. This is a generic formulation of a PDE where we're after a target field U, and we are looking at its derivatives with respect to time and space. Um, while while PDs are universal in almost all fields of science, solving them in complex problems requires computationally expensive numerical methods. So one of the similar lines of work in KGML is the framework of physics-informed neural networks, right? Where back in that was developed in 2017, and this article was published in 2019. Physics-informed neural networks, or PINs, use neural networks to solve PDs, right? For any arbitrary location and time, we can predict the target variable U by using the knowledge of the PD. And while pins can solve one instance of a PDE for a given initial condition and boundary condition, research in this area of using ML for PDs has grown. For example, in 2021, there were a series of works on neural operators, right, that can go beyond solving a single instance of PD to solving a family of PDs for any generic initial condition, boundary condition setting. We can now obtain solutions of PDs at arbitrary resolutions. Right? So there's a lot of work that is happening in the space of KGML for PDs. But there are many other forms of scientific knowledge that we have in many disciplines. For example, knowledge may be represented in the form of scientific laws, in the form of monotonic constraints, in the forms of rules, heuristics, and we are just showing some examples of research that are being explored in all of these different settings of this particular first dimension. Knowledge may be available in the form of symmetries or invariances, for example, rotational symmetry, translational symmetry. These are higher level properties that we know about a system. Right? And even if I know that that a system, even if I just know that a system respects a form of symmetry, can I just use this high level knowledge to build better KGML methods? Knowledge is available in the form of knowledge graphs, and we really see that especially in biology applications where we have ontologies. And finally, knowledge is also available in the form of computer programs that encode our knowledge of how processes work in many scientific systems, which can be referred to as mechanistic models. So here is just one example of a description of a mechanistic model for lake systems, where many times you would see that these models also have a modular structure, right? You have different modules capturing individual processes of a system that come together in complex ways to govern the underlying dynamics. And these boxes at the bottom are just showing some illustrative research in KGML targeting different formats of scientific knowledge. The second dimension is the type of scientific knowledge. So a researcher can ask whether their knowledge is available in perfect and complete form or whether it's imperfect and partial. So in some scientific problems, we can assume that we have the perfect knowledge of the system. Right? So for example, we may be interested in solving idealized PDs, for example, the Navier-Stokes equation. And given this equation, right, we can completely describe all of the dynamics of the system that we care about. Right? So if we care about the pressure velocity fields, solving the Navier-Stokes equation would can give us the complete information of the system that we are after. In this space of research in KGML, the primary objective of using ML is to see if we can improve the computational efficiency. And pins, depot nets, FNOs, they fall in this particular setting of this dimension. But in many other disciplines, knowledge may be available in imperfect forms, in the form of models that have approximations. They may have involved parameters that are not fully known, right? They need to be calibrated from data, which may have their challenges too. And in many problems, we may be missing the knowledge of some underlying processes completely, right? Or we may have simplified the model to make these models scalable for practical reasons. In such problems, along with improving the computational efficiency, the additional objective is to see if we can improve the accuracy of mapping the input drivers to the response variables. And some of the works that we have developed fall in this particular category, where we are using imperfect and partial knowledge. The third form, or the third dimension of KGML research is the very form in which we integrate knowledge and ML methods. This is a continuum where we have process-centric formulations on one side and ML-centric formulations on other side. When we're looking at process-centric formulations in KGML, the role of an ML model here is limited to fixing terms or learning parameters embedded inside a process-based model. So in this particular setting, the mapping from the input drivers to the target response variables is primarily driven by a process-based model, and the ML model is embedded within it to fix its deficiencies. The other side of the spectrum is where we can take an ML-centric formulation in KGML, right? Where the mapping from inputs to outputs is driven by an ML model, and scientific knowledge is used as a guide in varying forms to make sure that our learning is physically or scientifically consistent. This is really a continuum, right? We can have settings in this dimension that may fall in the middle, right? Where it's hard to say whether the ML, whether it's ML first or process model first. That would be the setting of hybrid modeling, right? Where both process-based model and ML model were in tandem, were hand in hand. The ML model may be fixing the process-based model, and the model may be helping the ML model learn physically accurate predictions. So this is the third dimension of KGML research. In the interest of time, let me talk about the remaining two dimensions as well, which is the fourth dimension is the method that we use for incorporating scientific knowledge in ML. Right? So regardless of whether we go for a process-centric formulation or an ML-centric formulation or somewhere in the middle, right? Whenever we have an ML model in a KGML formulation, we can ask how we can bring knowledge in the ML framework. And we can talk about three high-level settings on this particular dimension. We can change the learning algorithm, we can change the architecture, and we can change the initialization of these models, for example, neural networks using knowledge. On the first setting, when we are looking at knowledge-guided learning, an easy way to understand how knowledge can be brought in is through the use of knowledge-guided loss functions. So in many ML formulations, we are after optimizing a learning objective, which in many cases looks at a trade-off between minimizing the errors on a labeled data set or the empirical risk, and minimizing the structural risk encoded in the forms of statistical norms of model complexity. But in scientific applications, there is a possibility to add a third pillar of generalization performance, which is the consistency of the model predictions with scientific knowledge. This can be called as knowledge-guided, or on this particular slide, we are calling it physics-guided loss. The advantage of adding such loss terms is that they do not require ground truth observations. To check for consistency of model predictions with scientific knowledge, we don't need ground truth. So they can be applied even when we have unlabeled data, which in many scientific disciplines we have ample availability of. Um, Knowledge guided learning formulations have been explored for various settings, for the imperfect, incomplete setting, in the context of modeling lakes, and even in the context of perfect and complete settings, through the work of pins that are also looking at adding loss functions for solving PDs. But there are many other ways of bringing in scientific knowledge, for example, by changing the architecture of neural networks. You can encode invariants and symmetries directly in the neural network architecture. Popular example of a mainstream AI model that does that is convolutional neural networks that encodes our information about translational invariance, right? So if you have an object that you're after in an image, for example, a cat, regardless of where the cat is present in the image, right? A classifier, a convolutional neural network based classifier can detect the presence of the cat. But can we go beyond translational invariance to other forms of invariance that we see in chemistry and many other disciplines? So this is just some examples of research exploring this flavor of KGML. You can bring in knowledge in the architecture through many other ways. For example, in lake modeling, we have explored a variant of the LSTM architecture where the connections between the nodes in the LSTM formulation respect density depth constraints that are available in lake modeling. Or you can have a modular design to your neural network architectures that we have again explored for the context of lake temperature modeling. Or you can ensure that the hidden intermediate layers of a neural network express physically meaningful qualities. So this is something that we have explored in the context of fluid dynamics. The third setting or the third approach for integrating knowledge in ML is knowledge guided pre-training, right? For example, we can use process-based model simulations to initialize a neural network, right? Such that this initialized or pre-trained model can then be fine-tuned on very small amounts of observational data, which are limited in quantity in many domains. Right? Initialization is one way of knowledge-guided pre-training. There are so many other ways. Pre-training is central to the idea of foundation models. For example, in frameworks such as self-supervised learning, can we bring in knowledge guidance? Right? So there are some works that have been explored in hydrology. These formulations enable us to transfer knowledge from well-observed to less observed systems. Right? In systems where we have limited observations, we can perform few-shot learning by doing knowledge-guided pre-training. We looked at different methods for integrating knowledge in ML, and here is just one slide that compares the strengths and the limitations of these ideas. Knowledge-guided learning is quite generic to implement, right? You can, for many problems, we can think of constructing loss functions that adhere to scientific knowledge. And they can work with large amounts of unlabeled data. The challenge is that in many cases, they may enforce scientific knowledge in a softer way, right? Playing the trade-off between science loss functions and empirical loss may be challenging. When we go to knowledge-guided architectures, there is an opportunity to encode knowledge in harder or in a more embedded fashion, right? One of the advantages of knowledge-guided architecture could be that these methods can even offer explainability, right? So, for example, if you have a modular structure in our neural network, we can look at what each module is predicting, and that can help us understand the physical intermediates that we're after. The challenge is many times knowledge-guided architecture formulations get quite specific to a particular problem. So they are harder to implement relative to knowledge carried loss functions. Finally, knowledge carried pre-training enables us to transfer learning from well observed to less observed systems, can use large amounts of unlabeled data and even weak supervision, but they may not guarantee scientific consistency when they're applied um, just by themselves on new systems. And they do not directly offer explainability, right? But we can also mix and match these different ideas together, right? So these are not mutually exclusive. We can even have knowledge carried learning with knowledge carried architecture to use all their advantages. The fifth dimension of KGML research is the use case that we are solving in a particular scientific problem. Right? So how is KGML finally being used to solve a scientific problem? And there are different settings on this particular dimension, and they are certainly not exhaustive. So the first setting that has received a lot of attention is forward modeling. Given some input drivers and response variables, can we build ML models to go from inputs to outputs? And there are two different flavors of this particular setting. We can either have these models looking at the goal of improving the predictive accuracy, where we have some ground truth observations of the response variables, or we can look at the use case of surrogate modeling, where we may not have ground truth observations. We may just have simulations, simulation outputs coming from a process-based model. And the goal could be to improve the computational efficiency of these surrogate ML models. Quite the opposite use case of forward modeling is inverse modeling, where we are given data of input drivers and response variables, and we are also given a forward model, process-based forward model that involves parameters. The goal of inverse modeling is to estimate the parameters that, when fed into the process-based model, produces realizations of the outputs that match the observations. And there are many other scientific use cases of KGML2. For example, you can do reduced order modeling, which is almost like dimensionality reduction for process-based models. We can look at generative modeling problems where we are after producing distributions of variables of interest. We can look at equation discovery. So going from data of inputs and outputs, can we discover the underlying laws like the Navier-Stokes equation directly from data, and downscaling applications? And there are many other settings too. Just a note that this is not exhaustive. So this summarizes the 5 different dimensions that we just discussed of research in KGML. Here is just one table that contextualizes some examples of prior research in the space of KGML using this 5-dimensional view, right? And we invite the speakers for today, and more generally for people in the audience, to think of how these 5 dimensions can help them situate their KGML research. So these are certainly not exhaustive. These are just 5 or 7 examples. For each of these examples of prior research, we can see what variety of forms of knowledge that they have explored, ranging from PDs to scientific laws to symmetries, the type of knowledge ranging from perfect and complete to imperfect and partial. There are ML-centric formulations. There are some that are exploring process-centric formulations, different KGML methods for different use cases, and additional comments about them. Right? So we can keep adding to this list to understand where the gaps lie in current state of KGML research. So with that, I'll conclude. So we, just to summarize, we talked about this 5-dimensional view of KGML research, and we welcome feedback from the community on the structure. There are many future research directions. Some of these are listed over here. We want to explore how we can improve explainability, generalizability. How can we bring causality in KGML formulations? How can we do uncertainty quantification? So all of these are open problems. And in the light of the rise of foundation models, another interesting problem is how do we build foundation models that are anchored in knowledge using the principles of KGML. So, which is the precursor to Xiaowei's presentation. But I'll stop right here and happy to take any questions.
Nice talk. I think
maybe if you can use the mic.
You know, the community of CFD or on all those people, they have worry about the consistency of they're getting accurate results. They pay a lot of attention. So I'm looking at your forward modeling, inverse modeling, reduced order modeling. Have you done anything, study which methods or right type of things? Or I'm trying to figure out what is the way, because I dabble a little bit into reduced order modeling, so I know a little bit more about it.
Sure.
So what's your view on this?
Okay, yeah, that's a great question, right? So the objective of making ML models scientifically consistent is at the core of KGML, right? So it cuts across all of the different dimensions and all of the different formulations. There are some formulations that are more amenable to producing scientifically consistent results. For example, knowledge carried architecture, right? So if we hard code wire in scientific knowledge right in the architecture of these models, they would be consistent even if we perturb them. For example, if we are doing Monte Carlo dropout for uncertainty quantification. But we can also have softer ways of enforcing scientific knowledge to produce scientifically consistent results through loss functions. So there are different ideas, at least on the dimension of the method of integrating knowledge in ML, right? And these dimensions all work together for a particular KGML application, right? So for the different use cases of forward modeling, reduced order modeling, you can have knowledge guided architecture formulations, you can have loss functions, and even combinations of the two, right? So I hope that answers the question.
Anuj, thank you so much. That was a wonderful talk. Let me follow up on that question. So you take this philosophy that you add let me take that specific example.
Sure.
So let's say Raju is interested in incompressible flow, and so you have to make sure that over different subdomains, your flow is incompressible. In other words, the mass is maintained across, or the flux is maintained across boundaries. So your solution to that is to fit that into a loss function term. I think there was a term that you added there. And you could think of conservation of energy, conservation of mass, any of these as constraints. But a scientist would probably tell you that that's a constraint, not a loss term. And that makes your optimization problem impossible. In other words, if you think of that constraint is on the input-output variables, not on the model parameters. So when you're trying to do any kind of a gradient descent or even something smarter than gradient descent, it doesn't, I mean, it's not trivial how to do that if it's a constraint, not a loss term. So I don't know what your thoughts on that. And my second question perhaps is a more naive, simpler question. I think one of the things you started off by saying is that we want generalizability.
Yeah.
What forces generalizability? I don't see anything that forces generalizability or even introspects as to how generalizable a model is. And I suspect there are two different problems there. So those are my two questions.
Okay, yeah, thank you, Anand, for the question, sir. So let me talk about the second question first. So what promotes generalizability and how do we check for it? What forces generalizability? Right? So accuracy that we observe on training data could be one view of generalizability, something that is accurate on training data. We hope optimistically that it may work well on novel unseen testing scenarios, which would be the generalizability that we are after. But that may not always be the case. Right? Another way to think of generalizability or to think of what promotes or forces generalizability is models that are less complex, right? Which is going beyond, going back to the idea of Occam's razor, right? Even philosophical concepts that we need to keep our model simple. if they don't provide any additional gains in accuracy. So there is a trade-off between accuracy and complexity that is at the heart of machine learning. What KGML is bringing to the table is a third dimension of looking at what forces generalizability, which is scientific consistency. So a model that is consistent with knowledge or equations that we already know is hopefully more likely to work well or generalize on unseen testing scenarios. And this is what we have been exploring in different problems where we have lots of unlabeled data. All we know on those data instances is that the underlying knowledge, the equations, the laws should hold. Can we use that weak form of supervision to train our models? And if they're consistent with scientific theories, perhaps they have a better chance at being accurate with respect to the ground truth. So that's the philosophy of why we are exploring KGML. The first question was about loss versus constraints. That's a great question. So loss, I would consider loss to be a softer way of enforcing constraints. There could be constraint optimization problem formulations as well that we can explore, where we use them in a harder way. They of course can lead to more challenges, right? So that's the challenge that we have also observed in the knowledge guided loss or learning formulations, that making this trade-off is hard. Knowledge guided architecture certainly provide a way forward. So there could be, for example, divergence-free neural network architectures that would look at mass energy conservation in a harder way. But those are certainly future directions. Is there really a benefit? So if you go,
okay, I'm sorry. So if I've always wondered about this, and you can educate me. So once you get to that point of enforcing sort of a null divergence basis, you're pretty much in the world of what looks like finite elements, and all you've done is replace the finite element basis with a neural basis.
Yeah.
What is the win there? And I've never quite understood that.
Yeah. So one of the wins could be the ability to use GPUs to make these models scalable beyond what we have in numerical methods. So yeah, one of the advantages of using AI/ML surrogates is that they can be really fast during inference. So I think it's not that they would have the exact same aspects as a finite element model. They may have advantages of efficiency. There was another question.
So just following up on the constraints versus regularizer, it also has implication on learning algorithm, right? If you are just hung up on back propagation, which is a greedy, right, 200-year-old stuff, right?
Yeah,
it's not going to give you hard constraint satisfaction. It's not even guaranteeing very good solution quality. But in your whole discussion, you never bring up this learning algorithm. Should there be another dimension to your classification based on what kind of learning algorithm should be used and so on?
Certainly. So that's a great question. So learning algorithms are exploring knowledge guided learning, right? Which we have as one of the settings of a dimension. But the current progress that we see in the field with gradient descent only points us to more research that needs to be done. So we hope that by looking at problems in science, we can identify where gradient descent is lacking, and that can motivate us to develop better algorithms and look at the broader literature on optimization to do this in a better way. Gradient descent has its advantages, which is scalability for large parameter models, which is what we are seeing in the modern day. But certainly we can look at other approaches, and that's, I think, the intent to see what are the future opportunities.